Just like worse. And then walked off. Oh my God.
How's everyone doing? Leftover Halloween candy, if anyone's interested, just help yourself if you are. It is all chocolate though, disclaimer.
Yes. You should just bring the whole thing.
I'll just get a handful and put it in the bag.
Yes. It's more than I want to eat.
Yeah. Here you go. Can I trade you for Milky Way?
All right. Any questions from anyone about anything before we get started today? Oh. Main goal for today is finishing out Chapter 8, looking at the last couple rotational concepts I'd like you to be familiar with as part of the course. And that means that on Monday, we're going to start Chapter 9, which will be a short chapter on pressure and buoyancy. That'll be the last new thing we talk about before the test. So, when we have Test 2, which is in T-minus less than 2 weeks, we'll take it on Monday. Chapter 9 will be the last thing. It'll be on Chapter 6 through 9. And we'll have time next week to review. And also the week of the test to review as well. Once again, for today though, we finish out Chapter 8 looking at the last couple angular things that I want you guys to be familiar with. Those being angular kinetic energy and angular momentum. Any questions or concerns from you guys before we get started today? Yes?
Are we gonna have a practice test thing again?
Yep. Yeah, both tests and the exam, I always make a practiced test or exam that you can work on as study material, and I always upload an answer key for it as well.
Thank you.
All right, so on Wednesday, we started talking about moment of inertia, the idea that mass has an angular counterpart, since different masses will tend to rotate to different degrees based not only on the mass itself, but also the distribution of the mass, which is to say the shape of the object, and also the axis you choose to rotate it through. We had a whole chart of different moments of inertia for different shaped objects and different axes of choice. They're all basically mass times radius squared times some weird fraction. It's just a question of what weird fraction applies to which object. But you don't have to memorize that because you just have this table on your formula sheet. Now, I dislike moment of inertia, professionally speaking, but it is needed in order to consider several concepts in angular motion where they would normally have mass in their linear form. We already looked at force equals mass times acceleration. Therefore, torque equals moment of inertia times angular acceleration instead, just swapping everything for its angular counterpart. And the other couple formulas with mass up here, momentum equals mass times velocity, and kinetic energy equals 1/2 mass times velocity squared, also have I for moment of inertia in place of m in their angular forms as well. This one says angular momentum. I don't know why it's an L, unfortunately. Angular momentum equals moment of inertia times angular velocity, and angular kinetic energy, Ke with a subscript of theta, equals 1/2 times moment of inertia times velocity squared. And those will be the last two things that we're looking at, rotationally speaking, today. And despite how this slide is oriented, I actually want to look at angular kinetic energy first. If an object is moving, it needs energy, and that includes any possible form of motion. If something's moving in a straight line, it needs linear kinetic energy. And if its atoms are moving, that takes thermal energy. So all forms of motion, however small or weird, require some amount of energy, and that is true for spinning. The problem with spinning objects is the normal formula for kinetic energy has a linear velocity in it. What is this wheel's linear velocity right now? 0. It's not moving in a straight line. But does it have energy? It's not a trick. Does it have energy right now? Yeah, it's moving. You see it moving, it's just not moving linearly. It has energy because it's moving, and that energy is specifically in the angular kinetic form, because as it turns out, spinning takes energy, and a slightly different form of it to moving in a straight line. But it takes energy to get the wheel to do this. I have to grab the wheel and exert force and do work on it to get it to spin like this. If I'm doing work, I'm spending energy that has to go somewhere. It goes in the wheel in this form instead of the old one. So angular kinetic energy is 1/2 times moment of inertia times angular velocity squared, direct parallel to its linear counterpart, 1/2 mv squared. It takes more energy to spin it if it has more mass, if it has more radius, because I has m and r in it. So the more mass something is, the harder it is to make it spin, the more energy it takes. The physically bigger something is, even if its mass doesn't change, but its radius is just bigger, that's also going to take more energy to get it to spin. And it takes exponentially more energy to get it spinning quickly. Basically the same with its linear counterpart. Questions so far? All right. Now, what we're going to do with this for right now is note that there's kind of an odd interaction if an object is rolling forwards, which is to say, moving linearly and angularly at the same time. Hypothetically here, we've placed a sphere at the top of a ramp, and we've done questions like this back in chapter 5 when we were looking at energy transformations. I keep misplacing the good marker. I think it's one of those. Again, flashback to chapter 5, where we're talking about the energy of within a system and how it remains, the total remains the same from start to finish, even if the form changes. When we place this sphere at the top of this ramp, what form of energy does it initially have? Gravitational potential. It's located 2 meters above the ground, therefore it has GPE stored up that it could be using, but isn't yet. So before we drop this thing, it has GPE. What happens to that GPE is it starts moving down the ramp. It's going to lose that GPE, and what form is it going to turn into as it slides towards the bottom? Kinetic. If it's moving, it has kinetic energy. And if all it was doing was just sliding in a straight line, this would be the end of it. And we've done ones like this before, either for an object moving down a frictionless ramp or falling straight down. We've done things that look like this, correct? Notice though, in most of those previous examples, I never technically gave an object that was rolling. It was either sliding or falling. And that's because if it is rolling, there's actually another form of energy it needs on the final side. Because if it is spinning down the ramp, it not only has linear kinetic energy, it's going to have angular kinetic energy at the same time. So if it's rolling, it actually has to sacrifice some of its final kinetic energy to put into the angular form in order to roll. GPE total remains constant. This would be the same as long as it has the same mass at the same height. It could be a cube at that height, and this would be the same. If all it was doing was sliding down the ramp, it would only have linear KE, and we wouldn't care about this if it was just frictionlessly sliding on a single edge. But if it is rolling, spinning, it also needs angular kinetic energy at the same time. It needs both of them so that it can move both linearly and angularly simultaneously. If it only had linear kinetic energy, it would slide and wouldn't spin. And spheres don't usually do that on planet Earth because we can't turn friction off. Weirdly, rolling has to do with friction. If friction didn't exist, wheels wouldn't spin. So that's a weird thought. But if all this thing had was linear kinetic energy, it would just slide without rolling. And if all it had was angular kinetic energy, it would just spin in place, like when I hold the wheel. In order to roll, you need both. You have to sacrifice a little bit of the linear to give to the angular to actually keep it spinning. And that technically means there are some fringe cases where rolling is slower than sliding if friction isn't a factor. Because if you're not rolling, if you're only sliding, then this term isn't here. That means that you've got more energy in the linear kinetic form, and that'll drive your linear speed up. But if you have to roll, you're sacrificing some of that into this form instead. Like if you were only sliding, all of it could become linear kinetic, but if you're rolling, some of it has to become angular too. And that drives down the maximum possible linear speed. Now, in reality, this doesn't come up much because friction's a pain. Usually, in reality, when friction is factored in, it's still easier to roll than to, slide along the gravel ground. But in a frictionless world, sliding should be easier than rolling. Just weird thing to think about. What this means for this class is, in this specific situation where this is rolling down the ramp, rather than all the GPE becoming linear KE, we have to factor in a certain amount of it becomes angular, and that's going to affect the sphere's final speed. So we're now going to calculate the sphere's final speed once taking this into consideration. Does that premise make sense up here at the start? Okay. Now, first, I actually kind of quickly want to show what would happen if it was only sliding. We're going to take the angular out real quick just to do it the old-fashioned way, see how we used to do it if it was just like a box on a frictionless slope. So not rolling, just sliding, no angular yet. We're just going to see how that turns out. Remind ourselves how the old way worked. Initially, we've got GPE, so that's math. Markers annoying me now. How much time do I waste every day checking which marker has the most ink in it? I never remember to replace them because as soon as I leave the room, it's not a problem in my brain anymore. And I only remember when I'm in the room needing to use them. That's called ADHD. So, GPE initial, we've got mass at a height, and that's true whether you're sliding or rolling, really. Like, if you're sliding or rolling, that doesn't affect this part of things, really, because it's the same mass at the same height. And kinetic energy final, if we're only moving linearly, so we're not factoring in the rolling yet, we should just translate GPE directly into linear kinetic in a frictionless world. This sphere in particular has a mass of 1 kilogram. Magnitude of gravity on Earth is 9.8. Starting height was 2 meters. Mass is 1 kilogram. Solve for VF. Feeling familiar? And when we do it like this, I'm just going to put it over here. I'll write it as VF linear only. I got 6.26 meters per second. So 1/100th of stitch. Does anyone get that? So, just keep that in mind. That's what would happen if it was only sliding down a frictionless slope. Yes?
So you can just take the sliding velocity, and will that be the velocity you have for all of it?
Well, only if it is only sliding. What we're now going to do is we're going to take into account that if it is rolling, it has to sacrifice some of that KE to become angular instead. So we just did this kind of as a baseline. For true frictionless world, this is what would happen. Now let's factor in that instead it would roll down a plane with or without friction, really. So we're adding in that in our final state, some of the energy had to become angular kinetic. And the formula for that is 1/2 times moment of inertia times angular velocity squared. I'm going to write in omega final, the final angular speed at the bottom of the hill. If our goal is to find VF, this complicates things because there's now 2 unknowns besides VF. We need something for I, we need something for omega. What should we do about I? All right, what shape is this particular object? Sphere. That is our invitation to look over at this table in your notes or the back page of your formula sheet. Solid sphere, rotating through its own center axis, has a moment of inertia of 2/5 times its mass times its radius squared. And so that is what we can write instead of I. So you don't have to change your notes, I'm just showing, putting that in here. 2/5 mr squared in place of I. And that solves that unknown, because we know the sphere's mass and its radius. So that's I taken care of. Any questions for taking care of that? All right. Now we need to deal with omega, because what we want is linear final speed. Any thoughts on what to do with that? Now we want linear velocity, and that formula currently has an angular velocity in it. So we want linear, we have the angular. Recall that we are able to convert one into the other. Remember these from the middle column of the formula sheet? These allow us to transform any linear concept into its angular counterpart and vice versa. For the velocity, that means linear v equals the sphere's radius times its angular speed. Therefore, its angular speed is equal to its linear speed over its velocity, over its radius, sorry. So instead of omega, we can write this, which is both in terms of something we want and something we know. So I'm going to replace that omega with, and note, it was omega squared, so we'd have to square both the v and the r. Replace that with vf squared over r squared. And now, we've eliminated every unknown except vf once again. How's that feel? All right. So, find the new vf while factoring in rolling. All we have to do is plug our numbers in, but there's one quick thing I'm going to note to try to make our life a little bit easier. Our new expanded angular kinetic energy term has an r squared in its numerator and also in its denominator. So rather conveniently, those will just go away. So technically the size of the object doesn't especially matter for this, only its mass. Strictly in terms of its linear speed, the radius does affect its angular speed. But linear speed, the radius didn't end up mattering. So, noting that the r's cancel, I'm just going to leave them out because of that fact. To simplify this by one more line, 1/2 times 2/5 simplifies to 1/5 times the mass of the sphere times vf squared. Again, the r's canceled out. Left side simplifies to 19.6. The right side should simplify to 1/2 times vf squared plus 1/5 times vf squared. Both terms have vf squared in them, so we can add them together normally. I remember from when I did this earlier, 1/2 and 1/5 add up to 0.7. You can get there through the distributive property as well. And ultimately, please let me know if this is getting hard to read. Our final linear VF, factoring in that this sphere is going to roll down the ramp and has to sacrifice some of its linear kinetic energy into angular kinetic energy. Our new final speed is 5.29. That's about a whole meter per second slower. Having to roll down the ramp reduced the top speed from what it could be in a perfect frictionless world. But, you know, we don't really live in that kind of world anyway. In the world we do live in, even if it was sliding, we'd still lose a bunch of energy to friction. We'd have to find the work that friction does to take energy away here instead. And that would probably make the final speed even slower, So realistically, rolling is still more effective than sliding, 99.9% of the time. But again, weird frictionless world, sliding's easier. How's this feel? Any questions about this concept for right now? Yeah.
Why did you get the angle?
Sorry?
Why did you get the angle?
Oh. Because I borrowed this picture from a question that might have needed it, but it didn't end up mattering in this one specifically. If we factored in like how friction would act if it was sliding, we might need that because we'd have to figure out the physical length of the ramp to figure out, you know, force of friction times distance slid to figure out how much energy friction leaches away. But all we really compared here was frictionless to rolling, and we didn't end up needing to do that. Does that answer the question? Yeah, technically the angle of the ramp doesn't especially matter if it's frictionless or if you're rolling down it, and if you're only comparing initial GPE to final at the very bottom. All the ramp is really doing is making sure that your final velocity points this way instead of straight down if you were falling. All right. Last rotational concept. We're now going to look at angular momentum. Linearly, we talked about kinetic energy and then how it is both similar and different to linear momentum. So now let's follow up angular kinetic energy with angular momentum. Look at the formula first. Again, capital L is angular momentum on your formula sheet. And I don't have a very good story as to why that is, if I'm being honest. Again, physics ran out of letters a long time ago. Maybe it makes sense in Greek or Latin. And angular momentum equals moment of inertia times angular velocity, whereas linear momentum was mass times linear velocity. And the concept of angular momentum tells us that an object that is spinning wants to keep spinning with the same amount of angular momentum in the exact same orientation forever. Akin to how an object with linear momentum wants to keep moving in the same direction at the same speed forever. And it is how difficult that is to stop depends on, you know, the total momentum of the object. The more linear momentum something has, the harder it is to stop it from moving in a straight line. The more angular momentum something has, the harder it is to keep it from spinning at a certain speed in a particular plane. And like with linear momentum, angular momentum is conserved if the object goes through some sort of a change. Granted, angular collisions are a little weirder conceptually, but I am going to point out a time where this sort of thing applies. I'm going to get to that point. Right now, I want to look at this a little bit more again. Note again, if an object has linear momentum, it wants to keep moving in a straight line forever. And that's kind of all linear momentum says, because if it only points in one direction, the object is only going to move one-dimensionally until it is stopped, correct? Now the weird thing with rotation is it's kind of inherently two-dimensional in nature. Rotational vectors usually only point clockwise or counterclockwise. That's how we consider the vectors to point. But the act of rotating is kind of inherently two-dimensional because parts of this wheel are spinning in the horizontally in the x-axis, like any given particle of the tire is instantaneously moving this way up here or this way down here, right? But simultaneously on the very same tire, if I look at the sides instead of the top or the bottom, particles here are going either down or up, which is the y-axis. So this wheel, if we think about it as linearly as rotation can be thought of, this wheel is moving two-dimensionally at once. Parts of it are moving in both the x and the y at the same time. So it's more accurate to say that this wheel is spinning within a certain two-dimensional plane. If you kind of think of the flat board as a big two-dimensional plane, this is a separate 2D plane that's just, some distance away. So the wheel itself can be thought of as a 2D plane. And what angular momentum tells us is that this thing wants to keep spinning in the same 2D plane and will fight you if you try to change that. Like a normal object will fight you if you try to change its speed. Like if you try to slow down a train, you're going to have a bad time. If I try to make this thing spin in a different two-dimensional plane, it will fight against me. I will demonstrate. This is a stool attached to a rotating platform with as good a ball bearing as we can get to make it as slick as possible. I'm going to sit on this stool, I'm going to hold this tire, and I'm going to make it spin. And once it's spinning, I am going to try to turn it. I'm going to try to change the 2D plane it is spinning in. It's not going to like that. It's going to fight me. It's going to push back against me. And you're going to see what happens as a result. Okay, ready? I am not spinning the stool right now. The wheel is doing this as vengeance for me trying to turn it. I can even... It's running out of steam. I'm trying to turn around, but it's not letting me. Oh, there we go. I didn't do that. My feet are on the stool. If you don't believe me, you can try it out yourselves. When I try to physically move this around and change the plane it's spinning in, it will fight me. You might see that it's kind of wobbly in my hands while I do this. You can try that out too for yourselves if you want. It is literally pushing back against me while I do this. Like how linearly, if you try to slow something down, it pushes against you. Here, just changing the plane, it will push against you and fight you. And this is why, if you ever learned how to ride a bike, a tip you probably were told pretty quickly is not to do this with the handlebars. Does that sound familiar? Because when you do this, you are suddenly changing the plane of this tire a lot, and you tend to face plant. I hit a lot of pavement and a lot of mailboxes doing this. And instead, when you're riding a bike, you tend to just tilt into the turn slightly. That's again, the wheel wants to spin like this. If you make it change too much too fast, it fights you and bad things happen. Which, if you're 8 and uncoordinated, is not helpful. But this can get even weirder. Because it doesn't just fight against me and my hands, it'll fight gravity. Watch this. If it wasn't spinning, what would it do? It would just fall flat. And as it slows down, it's kind of heading in that direction. But while it's spinning, it will literally keep itself from falling over to try to stay in the same plane. This is how gyroscopes work, and tops too. They want to keep spinning like they're currently spinning, and will fight you to remain that way. So if something is gyroscopically stable, like drones or segways or anything like that, there's literally something inside of it that's spinning so that it stays oriented correctly. And the same is true for tops. If you spin a top and you flick it, it'll fly away from you, but eventually it'll right itself as long as it's still spinning, right? So angular momentum is the reason why. Additionally, you can also technically have a bike rolling forward with no rider because of angular momentum, because if the wheels are spinning, they want to stay up, even if there's no person. It's also the only reason unicycles work at all, and it's why you tend to fall over if you're not rolling forwards on a unicycle. So, pro tip for unicyclists, don't stop. Again, if you want to try this out for yourself, you are welcome to. I'm just going to leave the wheel up here. Now, not only is all of that true, another weird thing about angular momentum is it is also conserved like how linear momentum is in a collision. Angular collisions are kind of rare and weird though. Like sometimes you might have one spinning gear slot into another one, and you know the angular momentum of one is now shared with both of them. That is something that can happen. That's as close to an angular collision as I can think of. But there's another type of interaction that will demonstrate conservation of angular momentum. When we were doing linear collisions, linear momentum, note that one object would hit another and they will both still move within the same 2D axis. Their velocities would change spontaneously, but their masses wouldn't. We only really looked at changing velocities for those, right? That's because mass doesn't really change on the fly. Matter just doesn't vanish and reappear on its own. So, linearly speaking, velocity was the only thing that really changed in a collision from start to finish. But the weird thing about angular momentum is it's not just mass in the formula, it's moment of inertia. And moment of inertia depends on radius as well as mass. Every single one of these formulas, pictured here and on this page, they all have R or L in them. So it's not just the mass that matters, it's also the size of the object. And objects might not change mass spontaneously, but sometimes they can change size. For instance, a human can pull their arms in, and that reduces your effective rotational radius. You ever noticed figure skaters, how they can sometimes, they enter a spin with their arms and one leg out, and then they'll pull it in and start going around really fast? That's technically kind of an angular collision of sorts. When they're spinning like this, they have a certain amount of angular momentum. But when they pull their limbs in, their moment of inertia changes because their radius changed. And when their moment of inertia shrinks, their angular velocity rises to keep their momentum constant. And so they speed up really, really quickly until they throw their limbs out and exit the turn again. Sound kind of familiar? If you haven't ever watched figure skating, I am about to replicate this experiment, but not figure skating. One, I can't. Two, we don't have ice. Instead, I'm going to use a spinny chair. So, same platform as before. And to try to make it more obvious, I'm going to increase the mass of my body by holding these things. So I got 2 kilograms in each hand. What I'm going to do is, I'm going to sit in this stool, and I am initially going to hold these masses out at my full wingspan. That means that my moment of inertia is affected not only by my mass, but also this increased radius. This is making my moment of inertia bigger, because all the formulas are something times mass times r squared. So the bigger the radius, the bigger the moment, the harder it is for me to spin like this. So I'm going to hold my arms out and start spinning. Once I'm at speed, I'm going to pull my limbs in. And, well, you'll see what happens. Ready? All right. Spinning. Shouldn't hit anything. Note my angular speed, and I really shouldn't be doing this in a chair without a back. I'm going to do it in the other direction, because that might make me less dizzy. Okay, once more, and back out. And in and out. Speed control. Help. Fun fact, angular momentum is also the source of dizziness, because the fluid in your head keeps spinning even when your skull stops. At least that's what I was told. But that does mean spin the other way, and that should help it. So, between those two stages, my angular momentum stayed constant. But because I can spontaneously change my moment of inertia, my angular speed changes to keep the momentum constant. Does that track? Does that sound all right? All right. The very last thing we'll do today, we'll put numbers to what I just did. A person of mass 95 kilograms is holding two 10-kilogram weights. So their total mass is 125. Wait. No, 115 kilograms. They begin spinning at an angular speed of 1. I should have just given it in radians, hold on. Initial angular velocity is going to be 1 rotation per second, which is the same as saying 6.28 rad per second. While their arms are extended, and while extended, they have an effective diameter of 150 centimeters. They're then going to pull their limbs in and decrease their effective diameter and therefore radius to 55 centimeters. What will their angular velocity become if their angular momentum is conserved? So just like linear momentum, we're looking at conservation of angular momentum. That's going to be moment of inertia initial times initial angular velocity equal to final moment of inertia times final angular velocity. Note again, moment of inertia can change on the fly, whereas mass tends not to. We're going to treat this human as a solid cylinder just for simplicity's sake, because humans are a very weird shape, geometrically speaking. So we're just going to use the cylinder formula. So 1/2 times mass times radius squared. Note that the mass is not changing from start to finish. Only the effective radius of the person is changing from start to finish. So I've just plugged in the cylinder moment of inertia formula for I on both sides. That's not bad. And with that done, we know mass, we know initial radius, or we can find initial radius, we can find final radius. We know initial speed, so we can find final speed. Questions about the setup or the premise? All right. Kind of like last time though, we can actually do a quick cancellation here, because both sides actually have a 1/2 and an m on them, and the mass doesn't change, only the radius does. So actually, 1/2 and the m, we can just get rid of on both sides, divide both sides by 1/2, divide both sides by m, and we just don't have to deal with it. So it doesn't actually matter what size of the weights this person's holding. I had to hold the weights though, so that there was mass concentrated in my hands, because again, humans are not cylinders. So if you want to do this yourself, you should hold the weights. It would technically work if your hands were empty, but it's more dramatic if I'm doing this while holding the weights. All right, radius initial squared times initial velocity. This person's initial wingspan is 150 centimeters. Note that that's centimeters, not meters, and it's also diameter, hand to hand. We want radius. So not only does it need to be converted, we also have to cut it in half. So I'm going to put in here 1.5 over 2, and that gets squared. Make sense? Normally I just give you radius, but keep on your toes. Initial angular speed was 1 rot per minute, 1 rot per second, which is 6.24 radians per second. On the other side, the diameter shrinks to 55 centimeters. So that's going to be 0.55 meters, also cut in half. And we will solve for omega f. So, if this human was a cylinder, their velocity should increase. That's not the right unit. Their velocity should increase to 46.71 rad per second, which is 7 times faster, approximately. 7 or 8. Now, humans aren't cylinders, so it's not a perfect match, but it certainly felt like I was going 7 times faster. Questions? All right, that's it for rotation. We'll review and summarize on Monday as needed. Let me know if you need anything. Grab more chocolate on your way out. Try out any spinning things you want on the way out, and have a great weekend.